Welcome back. So, we were talking about the combustion chamber inside a gas turbine engine and inside an aero gas turbine engine, and as we have seen that that of course it contains of several components which are which has to be designed in a very precise manner and which has to be designed in an integrated manner, because as you have seen that the first component inside the combustor is your diffuser, and that diffuser has to be designed so that it can divert the flow in the required proportions into the dome region of the combustor, into the primary zone, as well as it can provide enough air in the same required proportion inside in exactly the same amount that it is desired into downstream region of the combustor, which is called the dilution zone. So, we have essentially three zones, as you have seen: the primary zone, the where the main combustion takes place; the intermediate zone, which increases the combustion efficiency and reduces pollution; and then the dilution zone. Okay. And we have seen what are the requirements of the primary zone, and this is how essentially the different kinds of flames in the dilution in the primary zone should look like, because in the primary zone what you have is essentially you have the injector, the liquid fuel injector, and on the liquid fuel injector is surrounded with the solar blades, okay, which provides the tangential momentum onto the otherwise axial flow. Okay. Now, why do you need this tangential momentum? Because when you have this tangential momentum, then what happens is that, of course, due to the centrifugal forces, the flow essentially diverges, and essentially when the flow diverges when the Soal number or the tangential momentum is sufficient, the flow can essentially recirculate. Okay. So, when it recirculates, essentially what you do is that what you are actually doing by making the flow recirculate is that you are increasing the residence time of the flow. And if you remember that in the earlier discussion on the limit phenomena, the S curve, that the Darm-Coulomb number, that is which is the ratio of the flow time scales to the chemical time scales, that should be substantially high for steady combustion to take place. Okay. If it is small, it can, you first of all you will not be able to ignite the mixture, and then even after you ignite, if it becomes small in certain cases after ignition, then it will extinguish. So, to have steady combustion, which is very much required, because if there is no steady combustion inside the gas turbine combustor, then you have basically no source of power, right. You do not have the chemical to thermal energy conversion taking place. So, you must have steady combustion inside the combustor at all times, and to ensure that your flow should not be at such a high velocity that it is not enough for the chemical reactions to take place. So, this is the very important and the very basic principle of a combustor design, that the residence time of the flow must be greater, okay, than the corresponding chemical time scales, which means that the Darm-Coulomb number should be high. So, to make the Darm-Coulomb number high, you employ this recirculation. In certain cases you can employ a bluff body also, as you will see later that typically in an afterburner or the augmenter people use bluff bodies, but in the main combustor, which we are discussing right now, okay, you essentially use this kind of swirling flows. And here the swirling flows is characterized by the Soal number, which is the axial flux of azimuthal momentum divided by the axial flux of axial momentum. Okay. So, these are the different types of swirling flows in laboratory combustor. Of course, you have to understand that in a real gas turbine engine, where the Reynolds number is of the order of turbulence Reynolds number is of the order of 50,000, then of course the flow is swirling, but it is also intensely turbulent. Okay. So, the flame essentially resides in a swirling turbulent flow. Okay. And then there are numerous things can happen. There can be nonlinear feedback, there can be feedback between heat release and pressure fluctuations, and these if they are in phase, then this can lead to instabilities. So, those are important things to be looked at, but in this course we will not go into thermoacoustic instabilities, because that is a very involved thing itself, and there are other NPTEL courses you can take a look for if you are interested in the thermoacoustic instability. So, in this course we will not cover that. So, then in the intermediate zone, you have to essentially ensure that the complete combustion takes place, and so the intermediate zone essentially provides enough air in combustion chamber to decrease the temperature and burn the carbon monoxide and hydrogen. And but typically, I mean, in modern combustor you go straight into the dilution zone, and this is the dilution zone. You see here what this picture depicts exactly what I was talking about, that the whole combustor should be designed in a very integrated manner. That is, you see the diffuser, you have to design it in such a way so that the 20% of the air is only going into the combustor. Of course, this actual number can differ for different combustors. This is just typical numbers, and out of that 20%, 12% goes to the swirlers. These are the swirlers, and then 8% goes into the surroundings, and then for cooling purposes. Whereas the 80% of the main air, okay, which comes out of the which exits the compressor, and actually or there can be, it can also be the bypass air. It need not be only always come out of the compressor. So the 80% of the total mass flow rate of the air that comes into the combustor is essentially diverted to the cooling purposes, which enters out of that 20% of that enters the 20% of that of the full air enters into this primary zone for cooling, and then later 20% enters into the dilution zone. Okay. And so first we need to essentially focus here that this purpose of this dilution air is that the exhaust that get out of the combustor is given a specific temperature profile before it enters the turbine, and this temperature profile is comes from structural considerations of the turbine blades. Okay. So that the material, because the turbine blades are under immense centrifugal forces because they are rotating at so high velocities, and not only they are under centrifugal forces, they are under both centrifugal as well as high thermal stresses. Okay. So to circumvent that, your temperature, and to maximize the life of the turbine blades, of course the turbine blades are one of the most expensive components of the entire engine. They have to be really manufactured in the manufacturing them is one of the most difficult challenges inside the gas turbine engine. And as such, then of course your as an engineer, your focus should be to design the turbine blades in such a manner that their life is maximized, and to ensure that their life is maximized, you have to ensure that the temperature profile that this turbine blade sees, average temperature profile and the fluctuating temperature profile that this turbine blade sees, they are exactly designed so as to minimize the thermal stresses, okay, or to optimize or you provide them a temperature profile which will maximize their life. Okay, and this profile is known as a pattern factor, and this dilution zone, this cooling is essentially achieved is designed to achieve a particular pattern factor, and essentially as you see the 60% of this air is used in here. Okay. So this is the 60%, 40 plus 20 60% that is used for achieving that thing. Now then we go into the details of the primary zone. Okay. We need to go into the some details about the primary zone, and essentially let us see what happens inside the primary zone. Okay. Now as if you remember that one of the most important goals, okay, one of the most important reasons why combustion is used in gas turbine engines is because of the immensely high energy density of the liquid fuels, right. Liquid kerosene or its variants Jet A1, Jet A, different types of this variants of kerosene are essentially used in the combustion chamber, which is the complete fuel source. So kerosene is the optimized fuel for gas turbine engines. Okay, and of course there the reason we don't use a battery in an aircraft, in a large aircraft, and we use fuel, liquid fuel, is because of the very high energy density of the liquid fuels. Fine, we understand this, but you see you cannot just burn the liquid fuel directly inside the gas turbine combustor. Okay, you just cannot have, because in gas turbine combustors, or the course so far we have seen, we have only talked about reactions in gas phase. In a gas turbine combustor also, even though we use liquid fuels, the combustion reactions strictly happens in the gas phase. Okay, they do not happen in the liquid phase. There are examples of reactions happening in the liquid phase. For example, if you talk about rocket engines where you use like MMH and RFNA for your fuel oxidizer, their reactions can happen in the liquid phase, which are called the hypergolic reactants. Okay, but in a gas turbine engine, in air breathing engines, in gas turbine engines, in afterburners, in scramjets, ramjets, everything. Typically when you use a liquid fuel, reactions must happen in gas phase. This is absolutely the always it's absolutely what happens in all occasions. So you have a tank of a liquid fuel which you are carrying, and then in the combustion chamber you are basically sending out the liquid fuel in some form. Okay. But so one important process is basically how you convert these liquid fuels into gas phase, so that this liquid fuel in the gas phase can mix with the oxidizer, which is the air, and then combustion can happen. Okay. Now you will ask that what is the problem? Okay. I will send out the liquid fuel and it will burn, and then I will allow it to vaporize or evaporate and it will burn. Okay. And then we can have it create a fuel and mixture, and then we can get it burning. The problem is that the time available in the combustor is not large, it is very short. Okay. So what you need to do is that we have to design a process by which we can send the liquid fuel into the combustor, and it can get converted from the liquid to the gas phase, to the vapor phase of that fuel very quickly, and in the vapor phase it can mix with the air and then it can burn. Okay. How do you achieve that? You cannot have we cannot just rely on the process of evaporation. Okay. So what we need to do is that this liquid that is stored in the fuel tank, we need to basically increase the surface area of this liquid to the maximum possible surface area. Okay. How can you achieve the maximum possible surface area? If you can somehow convert this liquid in the tank to very, very small droplets. Okay. Because as you know, in the droplets, droplet surface area by volume is equal to 4 pi r square divided by 4/3 pi r cube, right. So this cancels, so then this goes by 3 by r. Okay. So as radius decreases, the surface area to volume ratio increases. So for a given volume you can have maximum surface area if your radius is very small. Okay. And then of course we know that then this will lead to very fast evaporation also. Okay. So you need to increase the surface area. So for that you need to make very, very small droplets. How do you make very, very small droplets? And that is the process basically what is called the liquid jet breakup and atomization. So in this primary zone, apart from combustion, you have to have a very important process which is the droplet, the liquid jet breakup and atomization. Okay. So this is what we are going to study. So but recap that also we need a small droplets, because if you remember that the droplet vaporization time, okay, this droplet vaporization time was essentially proportional to the initial droplet radius divided by this droplet vaporization constant, okay, and it was given by this thing. It was given by this constant Kv was essentially given by this thing, okay. But all these properties lambda by Cp liquid so rho by rho L times ln 1 plus B droplet heat transfer number, with all these things you see that smaller the droplet, smaller is the evaporation time, and it goes like squared. So if you reduce the size of your droplet by 10 times, the time for evaporation reduces by 100 times. Okay. So the purpose a very important function of the liquid injector inside a gas turbine combustor is to produce droplets of very, very small size. The ultimate product of this thing is that I will take the liquid, I will connect this injector to my liquid tank in such a manner, in some manner, and then I will make some arrangements so that this injector can spray and can send out these liquids, and they can create a mist of very, very small droplets. Okay. But how does that happen? So this is also a very important fundamental part of a gas turbine combustor, and we are going to look into that. And even if the droplet burns, once again as you know that combustion happens in the gaseous phase, the time for droplet combustion is also proportional to the initial radius squared, okay, divided by Kc, where this is the droplet burning constant. Okay, this is the droplet combustion constant, which is also proportional to this kind of thing. So this is lambda by Cp divided by rho liquid times ln of 1 plus B Hc. Okay. So, the droplet heat transfer number for combustion. So, this is the thing. So, it is imperative that you produce very small droplets inside the combustor. So, for that, to understand that, we are fortunate in one sense that even if we send out a liquid jet, the liquid jet is not a very stable configuration. Okay. A liquid cylindrical jet is not the stable configuration, because of we will show that the liquid jet tends to minimize the surface energy, okay, to essentially tends to form small droplets, but that droplets are not it tends to form droplets which is proportional to the radius of that jet. Okay. So, we will see how that happens. So, we are fortunate in one sense, but we cannot only rely on that process, on the spontaneous breakup of a liquid jet process. So, we need to do something more to achieve even smaller droplets, and that will be called atomization. So, then the question, as you see here, this is what I am talking about, that we need droplets from liquid jets. How does that happen? It essentially happens by two processes: liquid jet breakup and atomization. Now, I will read this two paragraph because it is important that it was discovered by Plato that the surface energy of a uniform circular cylindrical jet is not the minimum attainable for a given jet volume. Okay. So, he argued that the jet tends to break into segments of equal length, okay, each of which is 2 pi times the jet radius. That means that it tends to form droplets, okay, which is which is equal to the circumference of the jet radius, or not droplets. It tends to break up into segments, and this length of these segments which it wants to break up is essentially equal to the circumference of the jet. We will show why it is so. Okay. Such that spherical droplets are formed, because once you break the jet up, even if it was cylindrical or distorted cylinder, it immediately tends to form a spherical drop from these segments, because that gives it the minimum surface energy if a drop is formed from the segment. You know that when a liquid surface is formed, then there is surface tension, which essentially tries to minimize the surface energy, and in trying to minimize the surface energy, it forms a spherical drop. Okay. And then Rayleigh showed that the jet breakup is essentially the consequence of hydrodynamic instability, which is called the Rayleigh-Plateau instability. And if we neglect everything, that is the ambient fluid, viscosity of the jet, and gravity, he demonstrated that a circular cylindrical jet is unstable with respect to the disturbance of the wavelengths larger than the jet. And among all the unstable disturbances, the jet is most susceptible to disturbance with wavelengths, which is 143.7% of its circumference. Now, where does this? It's important for you to ask this question, that where does this number 2 pi times larger than this jet radius 143.7% comes from. So, we will do the analysis of this liquid jet breakup, simplified analysis, which will show you that why does a liquid jet breakup happens. But this is very important. This is fundamentally, of course you understand that in a gas turbine combustor, when you inject a liquid jet, it is a very complicated process, because you have swirling flows, you have very high pressure flow where the turbulence is very strong. But once again, if you remove all these complexities and look into the very fundamental aspects, if you look into your kitchen sink and you allow the liquid jet to emerge, you will see that this jet initially stays a very laminar smooth jet, but at the end, after some time, it develops some distortions, and eventually droplets are formed. Now, this is what is called the Rayleigh-Plateau instability, and we will show that this jet can break up even when there is no gravity. Okay. So, we will do the analysis of this. And then you have atomization. Okay, this is also important, because we cannot, in the gas turbine combustor, we cannot rely on the liquid jet breakup process itself, and we cannot also, because there is so much air around surrounding it, swirling, or in high flow, high axial flow velocities, high tangential velocities, that you have a sufficiently large gas inertia force, which is proportional to the gas density relative to the surface tension per unit area of the interfacial area, and the jet may generate. That is what we want to say, is that if the gas inertia force is large related to the surface tension force, which is characterized by basically large Weber number. Okay, Weber number is defined in terms of the gas density. This whole thing is essentially called Weber number. Okay, and the jet may generate the liquid gas interface droplets with diameters which is much smaller than its own diameter, because you see here the droplet that will be formed is essentially of the order of the diameter of the liquid jet. Okay, but here when there is air, then the droplet that will be formed can be much smaller than these things. Essentially, you can think of it like the droplet is being peeled off from the jet surface, okay, by forming ligaments, etc., which is essentially teared off from the jet surface, and they form ligaments. And this Taylor mode of jet breakup is called the so-called atomization that leads to fine spray formation. So, essentially in the final jet that we have in a gas turbine engine, that contains droplets of different sizes. It contains droplets, a large population of droplets which are of the order of the jet diameter. It contains droplets which are of the order of the much smaller than the jet diameter, and due to different processes that are being involved. Okay. So, this is how an injector in a gas turbine engine essentially looks like, you see, and this is how this atomization process happens. So, this is the injector, this is the actual picture of the injector, this is a mesh, and this is a simulation. So, you see that this injector has different ports, okay, like this, and this liquid jet is coming out, and as you see that here it essentially this jet structure is maintained to some height, and then it breaks up into different form of ligaments, etc., into various different shapes. So, it is a very complex process, as you see, but once again this process is complex because the flow is also very complex. So, what we will do first is that we will take up this thing. This can be analyzed, okay. So, we will take up the analysis of this liquid jet breakup, which is called the Rayleigh plate instability. So, this in this thing, in this we have done essentially, if you remember, we have done, there are two parts. That first you have to do the jet breakup, and then once the jet breaks up, you form droplets, and these then droplets can evaporate, and this can mix with the fuel. This fuel can mix with the air, and then you can burn it. But first the jet breakup process is important, and then that is why we need to do it, okay. So, here is another slide before we go into the analysis. Here is another slide that shows you the different modes of how these small droplets can be formed. So, this A is essentially this Rayleigh breakup, where you see that this laminar smooth jet is coming up, coming down, where there is no disturbance, and then after some time small perturbations are essentially gets amplified into this, okay, and then this disturbance forms, and then you see this formation of these droplets which sometimes merge, etc., etc. And then there is a wind induced regime. Wind means essentially the surrounding gaseous flow. This can be a wind induced regime, this can be the second wind induced regime, and this is like atomization, where essentially very small droplets are peeled off from the surface of the liquid jet, and very fine mist is formed. So, this is primarily this liquid jet breakup and this atomization are the two basic modes by which small droplets are formed, but there are other more complex processes, different breakup mechanisms, bag breakup mechanism, etc., but those we will not cover in this is outside the scope of this class, and you should take a detailed course on atomization or sprays to understand that.